We're going to be talking about a little bit of a different topic today about managing large scale training data sets, especially for building foundation models and especially multimodal foundation models. This is going to be a little bit of a high level talk because I think the topic of multimodal data sets and training is a little bit off the beaten path for the usual sort of lakehouse and data architecture. I wanted to give everyone sort of a top level survey of what's happening. And then I'll give you some updates from the Lance community on the latest happenings in the Lance project. So super quick self introduction here. My name is Chang She. I'm the CEO and co-founder of LanceDB. We're the AI native multimodal lakehouse. I've spent about 2 decades building data tools, starting with Pandas. I was one of their original co-authors. I spent years at Cloudera working on Hadoop, and I spent years running engineering at Tubi TV, a streaming company, and that's where I came into contact with all of this multimodal data that is really difficult for traditional data infrastructure and tooling and formats to manage, and that served as the original inspiration for starting LanceDB. And our community is using Lance format and LanceDB to manage petabyte to exabyte scale AI data for training. And when I talk about AI data, what I mean is, embeddings, text, images, videos, and of course the tabular metadata. So all of that combined. Um, so at a very high level, there are three really big things that matters for managing this kind of data. So number one, for building models, if you're building LLMs or multimodal models, um, data is probably the most critical input, and also processing and managing that data is the least sexy task in modeling. And this is where we hear a lot of complaints from cutting edge research teams that they're spending way too much time actually managing the low level details about their data and the processing infrastructure rather than on core activities that advance the state of their model. Um, and I think while this was also true for the previous sort of classical machine learning era, um, things have changed and the problems are much bigger. So multimodal models tend to be and data sets tend to be much larger in data volume. With AI, data is generated at a much faster clip. And what's interesting recently is that agents are now drastically changing infrastructure requirements for processing all of that data. And all of this new data and these new requirements mean traditional data lake and lakehouse formats and stack becomes a blocker to research productivity. Infrastructure costs become prohibitively high, and also the stack itself become really really complicated. So it takes too many people, too many different systems, and too much energies to stitch together a stack on top of a traditional lake house. So to understand what that looks like, we can talk about the day in the life of a robotics, maybe like a robotics researcher, right? So if you're doing, if you're at an AI lab, a new smaller multimodal lab, or if you're in a physical AI company, a lot of the day to day is going to look the same. So for physical AI, right, we start with collecting the actual data, right? So action data that comes off the device with human labelers in a lab setup, and then we move into cloud data ingestion where we're converting all this raw sensor data and video data, and possibly audio, and then also just metadata about the devices. We want to put them all into a data lake in the cloud. And for large labs, we're processing petabytes, or at least like hundreds of terabytes of data every single day. Once it's in the cloud, then what we engage in is sort of this training loop, and more more accurately, it's the data set development and training loop. So step three here is feature engineering and quality control, enriching the data set, cleaning up that data, curating it, right, running quality checks, exploring that data set, making it ready, and then finally we ship a finalized data set into the distributed model process. Then to complete the loop, the output of this process is a new version of the model that then gets loaded onto devices, and then this loop continues again. Now, um, for when we're talking about lake houses and data, really the big focus, I think, for researchers is in this step 3 and 4 here, right? And this is what we call the data flywheel for model development. So we start with curation, where we are filtering the data, we're deduplicating, tens of billions of observations. We're doing distribution selection, creating materialized or non-materialized views on this data, and basically the task and the pain point is finding the 5% or even smaller, maybe 1% or 0.1% of observations that comes off devices that actually adds value. This number is much higher when you're running the first few model iterations, but as time goes on, this drops precipitously. So the task is how to mine for the right data. Um, Once you have some of that like reduced data set, you're going to start to enrich that through this feature engineering process. Maybe you are extracting metadata, you're extracting entities from images, you are creating embeddings, you're generating captions, you're extracting geospatial information. All of that means you end up with really wide tables, and the big challenge here is that you need to do really large data pre-processing without low-level infrastructure headaches, right? You want to be iterating as a researcher, you want to be iterating on your data set, and not your Kubernetes configurations or YAML files. And then once you have this enriched data set, the researchers tend to do a lot of data exploration, finding edge cases through search, debugging your data problems, using traditional sort of search and also SQL and data exploration techniques, right? And but this has to happen at really large scale data sets and on multimodal data. So, for example, traditional OLAP engines that does early materialization would be a really bad fit here, because it would mean that if you're storing the multimodal data, you would have to scan through the whole column before you're able to filter it and then return the filtered result set. Right, so big challenges in exploration as well. And then finally, in the training process, and this is a huge focus, right? So the ultimate goal here is to keep your GPUs really really busy so that you have high utilization, right? You've already paid for this really insanely expensive asset. You want to make sure that utilization is really high. And to make it more complicated, what uh, what you're required to do is you have a lot of more complicated processing and filtering and shuffling before data actually gets loaded into the GPU. So you might you might say, okay, I just want to invest in a feature where I'm loading directly from object store and like read it directly into the GPU as fast as possible. That sounds really cool, but is that useful? And the answer is like most of the time, not as much, because before that data load, you're going to do global shuffles, you're going to do a bunch of random takes. You may even need to do some ad hoc pre-processing and then you're going to load that data into the GPU. Almost never are you reading your data in order and you're scanning the whole data set directly into the GPU, right? So, um, but so that makes the challenge of high utilization really hard. And we can think about utilization either simply as GPU utilization throughout the training process, or MFU model flop utilization, which is a little bit more of a sophisticated measure that it measures a percentage from a sort of a theoretical ceiling rather than just absolute 100% GPU utilization. But this is typically the what we call the data flywheel for model development. Now, what are the so we talked about this process, and this process is now made even more interesting because a lot of the development process is done by agents rather than by hand, right? So, number one, if we're starting to do this, go through this data flywheel, writing data pipelines and transformations with agents instead of by hand, scale requirements are way up, right? So a few years ago, our RAG users and customers were looking at tens of queries per second, hundreds of queries per second. This year, we're talking to companies that need tens of thousands to hundreds of thousands of queries per second on just a single table. And this is because a lot of that retrieval is now done by agents, and agents can be massively parallel, right? The same thing uh, with thinking about second order effects is the requirements on latency. A few years back, uh, a few seconds or like under a second latencies seem to be fine. Everything is sort of one shot. Your time is maybe dominated by like the generation step or even embedding generation. So people didn't worry about it as much. But with agentic retrieval, low latency actually becomes more of a requirement because agents typically have much longer reasoning chains, and slow retrieval really adds up across multiple steps. Not only are the overall scale requirements up, but if you're thinking about iterating on models, developing models with the help of coding agents, your rate of experimentation is also up by a lot. It's going a lot faster. This is because for every feature idea, agents can immediately come up with a bunch of different variants in parallel and help you find the best one or the best set, right? So if you have um, two features, two intermediate features, each with maybe 5 different ways or 10 different ways to measure a particular score, and then you have a combination feature as a third one that combines the two. Well, that third combination feature is automatically going to have 100 variants, right? And then and each research, so your the rate of experimentation for your team is like number of researchers times the number of ideas they're having or the ideas they're getting from agents, and then how many parallel agents they can spin up to test their ideas, and then how many parallel variations these agents can handle. So this is kind of insane. And what does this mean? This means that the number of tables in the data sets that you have to manage and the number of columns you have to manage also goes way up, right? So, um, a few years back, if you're managing like a RAG data set or you're doing, uh, training data management by hand, you're looking at dozens of tables, maybe like hundreds if you were, really a large organization. And this year, we are regularly talking to teams with millions or tens of millions of tables. And I think our record is we've talked to our organization using LanceDB with 1 billion data sets that they're managing. So this is all coming from the power of using agents in the research process. So to summarize all these bottlenecks, sort of everything is bigger along every dimension because of multimodality and because of agents, right? So data volumes now are at PB to exabyte scale. Throughput is like tens of thousands, hundreds of thousands of queries per second. This is on up to that for a single table, right? Number of tables are also much bigger. um, and latency requirements are much higher, right? So what does it mean for data infrastructure? Horizontal scaling, you absolutely need that to handle this kind of scale. And it's not as easy to do for search. So table maintenance and index maintenance becomes much, much harder at this scale, especially if it's horizontally scaled out. And then, of course, the costs of this become the efficiency. I should say, becomes a huge item. At this scale, even small changes in efficiency, small improvements can mean a massive difference in utilization and in cost improvements. Right. And then the last one is data IO. Right. So if you had a few million vectors, you didn't have to be all that careful. You could read the data over and over again and not really impact performance, not impact costs at all. But if you have something like an exabyte of data, you really don't want to have to copy that data. You really don't want to have to read that data more than once into cache or something like that. And you have to be really careful about, essentially DDoSing your own data infrastructure, DDoSing your own uh, object store, right? And you carefully manage all this stuff. Um, so this is the backdrop in which we've designed Lance and LanceDB. Is we are creating a foundational solution to these new problems that are fairly fundamental to new AI challenges, right? So Lance format, it's a new lakehouse format that solves the foundational storage problems and makes it easy for the computational layer. And our enterprise data platform, it's the only, I would say, unified platform that allows you to solve all of these scaling problems across that whole data flywheel in the same system. I think today, because of our limited time, let's focus on the open source portion of that, which is the Lance Lakehouse format. Right. So we're going to quickly review Lance format. I think at this point, I think probably many of you have at least come into contact and know high level what Lance does. So I won't spend too much time on it. And then I'll give you an update for those of you who followed Lance for a while on the newest developments in the last few months, or which is, in my opinion, is pretty exciting. So real quick, Lance is the single source of truth for all of your AI data. Right? Training is not just about fast OLAP workloads. It's about fast random access. You need to do fast training, fast training scans, very large search indexes, schema evolution without having to copy the original data, and then of course fast data loading into the training process. Right, and Lance is the only format that supports all of these requirements. Every other format you adopt, it's either not a good fit for these workloads, or like it's a good fit for like one of them, but then you have to have additional tools and stitch together a bunch of different systems to complete your workflow. Right. So if you're thinking about placing Lance in sort of a lakehouse stack and overall ecosystem, right, kind of just remember Lance for AI and the combination of Parquet and Iceberg for kind of your tabular BI data. I think Lance open source, our community is really growing. I think we're fast becoming a new standard for multimodal data. Right, so we're at around $14 million per month. And for those of you who play Magic: The Gathering, we recently discovered this old Magic card from 1994 that is called Lance, and it's enchantment for any AI team that is enchanted by Lance. You gain first strike. Okay, so some quick updates on new happenings. We just released Lance Format 2.2, which we focused a lot on making it faster and adding encodings to make it a lot smaller. So what do we care about? Storage costs. We care about the random access of a large blob data, and then scan throughput for training, and schema flexibility for schema evolution and feature engineering. So you can follow this blog post. You can follow this blog post here for more details. But coming back, this is sort of the summary table here. So if we look at kind of comparison versus Parquet, it's about 52% smaller than Parquet for multimodal data sets. Typical data set, open data sets that you see in training. For blob access, it's about 70 times faster than Parquet. Scan throughput is we don't it's very competitive versus Parquet, and we do better at scale. And then schema flexibility, writing new columns and things like that, we're much faster than Parquet. So that's one big item. So when we talk about blob access, that's also really interesting. What we found is that previously, without Lance, most of our users were using external references and storing the blobs as individual files. This is really inefficient for training, and causes a lot of unnecessary read requests and high cost, and it slows down overall access speed. Right. So in a previous version of Lance, it was sort of all or nothing. Either everything was external reference, or everything was stored inline in the column. And what we found is that when you talk about multimodal data, there's actually a lot of variety in audio files or small images that are like hundreds of kilobytes, up to really large like DICOM images or videos that can be up to like tens of gigabytes and hundreds of gigabytes. So we wanted to be able to separate that access API from the storage interface. So that's what we did in Lance v2 2.2, which is the new blob API. There's multiple underlying storage strategies, but the same access API. And you can sort of look at this blog post for more detail. So for our users that are dealing with lots of multimodal data, that they're dealing with a wide variety of them, this is going to be a huge improvement for performance and scalability, and managing memory, and managing compaction and table maintenance. Okay.
We should put that link down in the chat as well, by the way, for those who didn't catch it yet. I think it's going to be a
Yep.
fascinating one to read. Nice. And
Um,
Chang, I will say, if
yep.
people have questions, now is
Yep.
a good time to ask them, because we should be wrapping up now, but I want to make sure that we leave a couple of minutes for people with urgent questions.
Sounds good. Yeah. And basically, I just have one more slide here. That the last one, when I talked about experimentation being a lot more frequent with agents, this is another area where we invested in Lance format, is a better branching strategy for ML experimentation. And we kind of combine the best attributes from how Iceberg does it and how Delta does it into sort of branching plus shallow clone strategy for Lance. So it's really optimized for rapid ML experimentation. And of course, I can put some of those links down in the chat as well. So, and then I will just finish up. So thank you for coming to my talk. We are hiring, so scan this QR code if you're interested in working on something cool.
Something cool indeed, Chang. I've been following your guys' work for many years, and it's consistently cool. So thank you for coming and for doing the presentation. And I feel like a lot of us have just an intuition that scale is up, but we can't really identify the components of the scale. And I think you've done a really good job identifying just all these agents implementing ideas that all these engineers have. And each of these is just its own experimentation, and they're pinging these tables, and now these tables can reach millions. It just sounds like a completely different reality. So wild that you guys are operating in that space.
Yeah, it's a wild world right now.
And I think probably resonating with that intuition, we got a question. I'm not sure if to make it a question or how to take it, but how do these companies keep up with these things? I mean, like, they're working with you guys with LanceDB. I think it was in reference to that scale slide. Somebody, I think it was maybe Jennifer, was asking. It seems like things are moving too fast. How do people keep up?
Yeah. I think so. My tip is actually
By
uh
the way, the QR code that you put up is disabled,
oh,
people are saying.
sorry. I will. I'll put up a new one in the chat
Cool.
right after this. Um, so what I would say is the reason why folks have problems keeping up is because AI is moving so fast that a lot of teams I talk to, they're like, well, I have to essentially, like every quarter, the model capabilities are experience a step function. And as a result of that, then totally new frameworks and new patterns come into being. And then I essentially have to totally redo my AI stack from top to bottom every 6 months. This is sort of a common refrain, especially in the Bay Area. And um, I guess in our experience, the only way to deal with that is sort of try to understand what are foundational layers that don't necessarily change. It's,
Mm,
what's a constant? Like, hey, your data is kind of a constant. So if you can figure out uh, you can have a stable way to deal with your data and the context management. And if you have a stable API abstraction layer that then allows you to say, hey, maybe the application layer or the agent framework that I can change every 6 months. That's not a problem, right?
mm,
And especially with agents, changing that every 6 months is less of a deal. But like all of the other stuff that's like difficult to move and hard to change, I can actually still make it stay the same and
mm.
have a consistent and sane interaction layer. I think that reduces a lot of the work of like
Yeah.
trying to keep up.
Yeah, you're basically identifying those sources of stability and leaning into those,
Y-
expecting the rest of the world to continue to move fast.
Yep.
Yeah. We got one more here. I'll put it up on the stage regarding multi-process concurrency. Are there any challenges in handling of S3 log files?
Less so the lock files, but with these large data sets, the big challenge is that it becomes really easy just to like hit the bandwidth limits of an S3 bucket. And so that's actually so the strategy that we have is we allow folks to stripe a single Lance table across multiple storage accounts. So
Mm,
that way, if your S3
mm,
bandwidth limit is like 100 gigabytes per second, you can stripe that like 10 petabyte table across like 10 different buckets or 5 different buckets, and you can get a lot higher uh bandwidth out of that. So
That's
I would say like that's the biggest
that's a
problem
cool
that
hack. Nice.
yeah.
Nice. Awesome. Chang, thank you very much. I do think that they put the career page link in the chat already.
Okay.
So, but feel free to linger in the chat because we do have a few more questions that we didn't get a chance to ask. So, Chang, thank you very much for joining us.
Thank you, Adam. Thanks everyone.